Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
So a large rock is dragged through thick mud by a rope. The mud exerts a resistive force, F sub r equals minus k times v, where v is the velocity and k is some constant that represents how resistive that force is. You pull the rope with a constant force F naught. Use Aristotle's incorrect law of motion, that F equals m times v, to model the motion of the rock through the mud. Part A, derive an expression for the velocity and the position as a function of time of the rock. Part B, what is the terminal velocity of the rock? And Part C, what is m in F equals mv? And finally, Part D, what conditions does this approximate the true motion of the rock? So if you're not familiar with Aristotle's notion of dynamics, it was basically that the velocity of an object is proportional to the force applied. And this made a great deal of sense back in his time because everything was very resistive. If you had a cart that you needed to push, the harder you push, the faster the cart moves. So it made a lot of sense to them back then. But of course now we know that this is incorrect. We have Newton's laws of motion, which are far superior and actually correct. But in some instances, however, Aristotle's law of motion can be useful. So that's what we're exploring in this problem. So I'm going to give you an opportunity to work on this, and in a week or two, I'll post the follow-up video with the solution. Okay, welcome back. I hope you had some success with this problem. But let's go through and try to answer it now. So we're going to approach this using kind of our modern sense of analysis, and we're going to think that this rock that we're pushing is going to apply a force F naught, and it will be resisting with a force F sub r. So we're going to use the sum of the forces equals, and using Aristotle's incorrect law of motion, it's equal to this m term times the velocity. So the sum of the forces in this case is F naught, and these forces are, of course, vector quantities, and F sub r is oppositely directed to F naught, so this will be minus k v. And this will be equal to m times v. Now it's just a simple algebraic problem. We can solve for v to get that v is equal to F naught divided by k plus m. And if we wanted an equation for x, it would just be the integral of dx dt. This would be equal to the integral of F naught over k plus m dt. Since there's no explicit time dependence in F naught, k, or m, this would just be equal to F naught over k plus m times t plus a constant, of course. Part B, what is the terminal velocity of the rock? Well, notice that the velocity does not carry an explicit time dependence. So the terminal velocity is the only velocity. So in this case, the terminal velocity, v sub t we'll call it, is just equal to F naught over k plus m. All right, part C asks, what is m in F equals m times v? Well, it's not mass, if that's what you're thinking. Certainly, you can think of it as a thing that is resistive to motion. So if we were to look at this a little bit and think of it like this says velocity is equal to the force divided by this m term. And so the larger m is, the lower the velocity will be. So if we have a big cart, if we have two carts, say one is bigger than the other, the first cart, when we push it, we'll be able to push it faster because it is a smaller cart. The second cart, which is larger, will have a slower velocity because of its increased size. And so we can think of this m term similar to what we normally think of as the mass of an object, but notice the units don't work out. If we look at the unitary analysis of this, we get that force, which we know from Newton, as terms of kilograms meters per second squared, and this is equal to these unknown units of mass times velocity, which is meters per second. So we would have agreed with Aristotle on the units of mass, or we would have agreed with Aristotle on the units of velocity. It's some distance per time. Force would have been a kind of an undefined or unfamiliar concept in the sense of it having units. I don't believe that Aristotle assigned any units to force. So in that sense, he could have thought of m as a mass term. That would have just meant that the force would have different units than what we have today under Newton's law. But if we're going to try to show how this can be an approximation to Newton's laws, then we'll need to relate these two. And so just to get a feel for what this mass would actually be, solving for this, just doing the unitary analysis, we see that the mass will have units of kilograms per second. And what it does is it tells you, it describes how much force is required to maintain a certain velocity. All right, and then the final part of the problem, what conditions does this approximate the true motion of the rock? Well, in order to figure that out, we're going to have to calculate what the true motions of the rock are. So let me just make some room here. Okay, so I've highlighted our key result here, that the terminal velocity, according to Aristotle, it's also the only velocity, is equal to F naught, the force that we apply, divided by K plus M. So to distinguish the m's in Newton's laws, instead of using m, I'm going to use mu for the mass. So Newton's law would say F equals mu times dv dt, or mass times acceleration. When we sum the forces up, that will be virtually the same. It'll be F naught minus kv, but this time, instead of being equal to mass times, or m times velocity, it's going to be equal to mu times dv dt. This is just Newton's second law. Now we could, of course, solve this differential equation, but we know it's going to have a velocity that's dependent on time, and so it's not going to compare well with Aristotle's. However, if we look at the terminal velocity, so how do we figure out what the terminal velocity is? That's fairly straightforward if you're not familiar with the idea of terminal velocity. If I drop something, at some point, the air resistance will balance out the force of gravity, and it'll stop accelerating. And when that happens, we call that terminal velocity. And so what's representative of it is that there's no more acceleration. That means that dv dt goes to 0. And so we end up getting that F naught is equal to k times v, which means that the velocity, the terminal velocity, is equal to F naught over k. And so if we compare Newton and Aristotle, terminal velocity under Newton, F naught over k. Under Aristotle, terminal velocity is F naught over k plus m, where m is this kilograms per second term, this resistive component in his incorrect equation of motion. So you can see that in the event that the resistive constant k, that's the resistive force that we get from the mud that we're dragging the rock through, if that is large, sufficiently larger than k, then Aristotle's equations of motion are a good approximation to the true equations of motion. Since they're very simple, they can sometimes be useful in that context. So, in the event that you have a very high viscous force, the approximation F equals some m times v is an okay approximation to the true equations of motion. Well, I hope this problem was a fun exploration, and I look forward to giving you more problems in the future. Thank you.